So I've got the function f of x equals 9 over x, right? And of course, whenever I give you a function, you should put it in your calculator, right? So hopefully we're just kind of building up a library of what do functions look like, right? So any kind of 1 over x will look like this. And we are interested in the fixed point of 1 comma 9. And so what we're going to do is we're going to find that secant slope, but we're going to be looking at positive values of h. So for example, this is 1 plus h, right? And this point here is 1 plus h comma f of 1 plus h. And we're interested in the slope of that secant line. What we're really interested in as we move toward calculus and beyond is the slope of the tangent line. So I want to kind of imagine, I want to pretend that h will go to 0 and the difference between the points will go to 0, right? The distance between the 2 points will go to 0. So meaning the point might move to here and then to here and then to here. But what I'm really interested in is the tangent when it only hits once. The slope of the secant line is the average rate of change. It's how fast I'm going on the whole trip. And the slope of the tangent line is the instantaneous rate of change. What's my speed at any exact moment, right? Like when the speed camera gets me, right? So let's first find our difference quotient. So you're not really copying me here. You're doing the work yourself, right? And let's see if we get to the same place. So my difference quotient here is going to be 9 over x plus h minus 9 over x all over h. Everybody with me? Idea? So we're doing the difference quotient. When we're doing a difference quotient with a radical, we're going to use a conjugate. When we're doing a difference quotient with a polynomial, we're going to be factoring. And we're doing a difference quotient with a rational function, fraction, we're going to be doing an LCD, right? So I get my LCD, or common denominator is probably better. I multiply by 1 by using the common denominator over itself. I distribute, I cancel, I rewrite, I simplify. Now you can see I'm back to a polynomial. I've cleared fractions. What's called is I no longer have fractions within fractions. And so now I'm back to that polynomial stage, but again, you'll see that every term without an h in it will go away. Better yet is saying the only terms left will have a factor of h. Anyone get there?
Yeah, I got there.
Nice.
Yeah, got it.
Nice. So once we get our difference quotient, we're going to fix an x value. So notice that the only variables we have here are x and h. But we're going to fix that x value at 1. X is 1, right? So I'm really thinking of m sub sec, the secant slope, right? M meaning slope, sec meaning secant line. And I've got the point 1, 9. That's my x1, y1. I also have the point x plus h, so 1 plus h, right? So 1 plus h, comma, f of 1 plus h, which is not that difficult. This is my x2, y2. Right, so I certainly could rewrite that as 1 plus h, comma, 9 over 1 plus h, right? That might be a little bit confusing, but I'm hoping you're okay there. Right, looking at my picture again. Right, I had an x and an x plus h, but I had fixed the x at 1. So I had the point 1, 9, and they have the point 1 plus h, 9 over 1 plus h. And there's the secant line I want. I almost hit it. So I can actually calculate the slope now, right? 2 ways. I can use my 2 points. Better yet is for me to use my difference quotient, the difference quotient I got. So I know my secant slope, and will you remind me what I get? What did I get? What did I get for my difference quotient? I got it. Don't tell me.
-9 on x plus.
Nice. So -9 over x times x plus h, but I know the x value, right? So my secant slope at 1, h is -9 over 1 plus h. And this is what I'm going to use as my secant slope. And so what am I doing? Again, I'm taking that red secant line and moving points closer and closer together until I get the tangent line. Right? The tangent line is the line that hits once in purple there. So what they're asking us to do, and what I typically do, is a little bit different than what they're asking, but to give me positive values of h that makes sense, so I can kind of predict what happens when h becomes 0, right? So x for us is always going to be 1. H for us, they're saying 0.5, right? They're using 1/2 and then 1 over 10 and then 1 over 100. I typically will use 1, 0.1, 0.01, and 0.001. Once I get to gas station money, I should be able to make my prediction. It should be very, 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 very clear what's happening. And we want to look at the m sub sec here, right? The secant slope. So I'm now just plugging those values into h, right? So what's the first one? -9 over 2. What is that? 4.5? -4.5. -9 over 1.1. So -8.18 repeating. Oh, I did that. Did I do that right? Yes. -9 over 1.01, right? -9 negative 8.90890. So that's repeating. And then negative 9 divided by 1.001, right? And so I can kind of tell where it's going, can't I? I mean, I think you can. You're going to see that it's clearly going to 8.999 and then 8.9999. You know, who cares what's happening after that? But I can see where it's going. It's going to negative 9, right? So this limit, the limit, of and the slope of the secant line as h goes to 0 is negative 9. So that's the slope of the tangent line. This is calculus, by the way. And you say, well, I mean, I can handle this, so why not just teach me calculus now? Because we have to keep doing all of this with all types of functions. That's the issue. Is I need you to be kind of a master of trigonometry and exponentials and logs and inverse functions and, you know, polynomial functions and radical functions and rational functions. So we're going to be doing these kind of processes over and over with all these different types of functions until you've really hopefully mastered them, so that when you go to calculus and they bring up any function, you'll have no problem with it. All right, let's go to the graph. How are we doing here? We're comfortable with what's happening. So we know we calculated the slope of that secant, then the next secant, the next secant, the next secant, and finally we're just going to predict the tangent slope, right? And of course I can't calculate the tangent slope because it's only got one point on it, right? That's the interesting thing here. So this stuff I'm going to do on Desmos. Obviously, I can't ask you to do this on the test, but I want you to see what's going on here, right? So I'm in Desmos, and I want to graph my original function. I got to do a little bit more work before I really finish up with this, but I'm going to go y equals the 9 over x, right? And I already know I have a fixed point of 1, 9, right? 1, 9. And so I can see my fixed point on there. I want to have some future point of 1 plus h, right? So I think I can put that on as well. So I have 1 plus h, comma, f of 1 plus h, which is just 9 over 1 plus h. 9 divided by 1 plus h. And Desmos is asking me for a slider, and that slider will allow me to change that point, that second point. Right? Kind of cool. I can see the fixed point where I want my tangent eventually, and I can see the second point of my secant line, and I'm going to graph the secant line through there. Is everybody with me here? You okay? Nice. You know, and if the brain hurts a little bit here, that's pretty normal. Okay. But just try and stay with me. So I want to graph the secant line here. Okay, so I'm going back to my paper just so I can do a little bit of work. I know I have the 2 points, I have 1, 1, sorry, 1, 9. That's my fixed point. I'm calling that x1, y1. And I've got my second point of 1 plus h, comma, 9 over 1 plus h, right? And when that function is nasty, that gets pretty nasty as well. So that's x sub 2, y sub 2. I've got my slope of my secant of negative 9 over, help me, I forget already. Oh, it's right there. Negative 9 over 1 plus h, right? And I've got my slope of my tangent, tan, tangent of negative 9. So I want to draw in my secant and I want to draw in my tangent. Okay. For both of them, I'm going to use my equation y minus y sub 1 equals m times quantity x minus x sub 1. Right? This is my new friend. If you only like the y equals mx plus b, you gotta forget about 8th grade and come and join the rest of us here. We want to be using this equation of the line for the rest of our mathematical lives. Of course, we'll use the other one as well, but so on this one, I'm going to use my x1, y1 and my secant slope to get the equation of the secant line. So here is the equation of the secant line. So I get y minus 9 equals negative 9 over 1 plus h times the quantity x minus 1. It's a little bit strange, I know that, but hopefully you're okay there. And now I'm gonna go to Desmos and graph this. This one's not really. It's possible to do on your calculator. It's not easy. So I'm putting in that equation here. What was it? Y minus 9 equals negative 9 divided by 1 plus h. Remember, I have my slider h working all times quantity x minus 1. Oh, and I made a mistake. Y minus y minus 9. There it is. And you can see my secant line in red going through the 2 points. And as I change h, right, as I change h, my secant line will change. As I change that value of h, the secant line changes. How are we doing? I got a couple of nods, couple of thumbs up. Thank you, Brian, Yvonne, Aiden, Oscar, Isaiah, thank you. Now, I also want to graph my tangent line, right? I want to say, well, what's going to happen when the 2 points become a single point, right? When h goes to 0, what happens when the distance between the points goes to 0, right? Of course, you and I know we need 2 points to get a line, but this is the magic of calculus, that I can actually get a line with 1 point. And so I want to be working on here the equation of the tangent line. So the only thing that's going to change is my slope. So I'm really done. Y minus 9 equals negative 9 times quantity x minus 1. And I can go right there. Of course I could simplify it, right? Y minus 9 equals negative 9x plus 9. Y equals negative 9x plus 18. So there's my mx plus b version. And so I'm going into there, and I'm going to put my tangent line in. Y equals negative 9x plus 18. And there's the tangent line. Let me just change the color of that. Forget how to do it. Oh, it's over here. Nope. I forget how to change the color. I think if I just graph it again, I forget how to change it, but it'll give me here. Now it's green. That's fine. So the tangent line's in green, and it's hard to see it, but you can really see that the tangent line's just hitting at one single point on the blue curve, right? The curve 9 over x. And as I change my value of h, my red line, which is my secant line, is going to become the tangent line. As h goes to 0, the secant slope becomes the tangent slope. The secant line becomes the tangent line. Boom. There it is. That's about as difficult as it can get on the first test. And maybe proof by induction might be tough as well, but that will be extra credit. A proof by induction problem will be extra credit. Nice. So as we move forward today, well, first of all, any questions here? Anything? Nice. So we can move on. We're gonna. I think we can cover 2 homeworks. We'll get to up to 2.4, and then we'll leave one last homework for Friday. So I'll probably be starting chapter 3 on Friday. So if you can read 2.5 ahead of time, and then even try and jump to 3.1. There is a section 2.6, but I'm not doing that. Okay. So we've got 2 things to talk about here in chapter section 2.4, and they should all be a review. Okay, the first one is horribly easy, and the second one is not so easy. But in the first one, we're talking about intervals and points on a function on a graph, and then the second one we're talking about piecewise functions. So that one sucks a little bit, but the first one is very easy. So we're looking at, let me just jump right to the homework. There's no lecture to do here because it's so easy. There's nothing really to do here. Nothing to teach you. You should have either done this in Algebra 2 or Math 50, right? So if the last thing you did in high school was Algebra 2, you did it there. If the last thing you did at Montgomery College was Math 50, right, then you did it there. And if you didn't, let me know, and I will go yell at those teachers. Oh, so 2.3 is my intervals and points. So I'm just going to jump right to it because it's so easy. It's it's painfully easy, and I'm sorry if it's offensive. But I'd rather you be offended and be able to do it easily. Now, am I going to ask a question like this on the test? No. But it's something you should be able to do for future things. So don't skip it. So this first question here it's asking, is the function increasing on the interval from -5 to 2? And it's pretty darn obvious, right? So I'm looking at the picture here, and I have from -5, I think it's -5 to -2, -5 to -2, and the function is doing something like this. And so it's just asking, left to right, am I walking uphill, right? So the function f is increasing on -5 to 2, -2, sorry. And this book uses closed brackets. I don't agree with the closed, the inclusive. In Calc 1, in your Calc 1 book, whenever you talk about increasing, decreasing intervals, you'll always be using open intervals. So I don't know why the book uses this. But I like to think of it as I've got the sun above me here, right? And it's casting a shadow down on the floor. And I want to know, as I walk up that piece of the graph, do you see that my shadow is cast down between -5 and -2 inclusively? And that's what we're trying to see, that this is always a subdomain. Right? It's a piece of the domain. So whenever I'm talking about where is a function increasing, I'm talking about left to right going uphill. If I'm saying decreasing, I'm talking about left to right going downhill, right? And so I'm just asking you to look at a bunch of problems and see if you could see, right, where the function's increasing, where it's decreasing. And we get the algebraic version of this in Calc 1. So in pre-cal, we're saying, well, can you see it? And then in Calc 1, we're going to say, can you find it? Right? Which is much more interesting than just looking at it. So there's not many more problems than this in this particular section. Is everybody understanding here what I'm talking about? Thank you. Thank you. Thank you. I appreciate the cameras on. It's so easy to communicate without even saying anything when you have your camera on, but then the rest of you are giving me the thumbs up, right? I always said there should be another icon. You know, you should be able to give the teacher this icon every now and then, I think. But they didn't put that in there. I don't know why. All right, let's look at another problem here. Is it increasing on the integral from -5 to 0? -5 to, is this particular function increasing? Am I only walking uphill when my shadow is casting on the x-axis from -5 to 0?
No.
No, right? So it's kind of insulting, but it should be a 5-minute homework for you. Is there a local max at -3? So when x is -3, and you can always hit this bigger, there's a pop-out icon for the graph. So you can always put that, show that one if you're having trouble looking at their grid. So, but at -3, do you see I'm at the top of the hill? And that's what a local max is, right? Just because we're both climbing a mountain and I'm at the top of this part and you're at the top of this part, yes, you're higher than I am, but we're still at the top of a hill. And that's what we're talking about with local max. Local min would be at the bottom of a valley, right? Absolute max would be the absolute highest point, which I guess is what, Everest? The very top of Everest on the Earth. And I think the lowest point is underwater, so no one's going to be standing there. But the absolute max means there is no other higher point, right? But we're talking about local. Locally, am I at the very top of a hill? Yes. Oh my God, I'm so bored. I'm sorry, I shouldn't say that. Do other teachers tell you when they're bored? No?
I think you're the first.
I'm ADD, so I can't lie though, I can't pretend this stuff is exciting. It's not. There is some great stuff you're going to see. So, but every now and then we have to do something horrible like this. Every now and then you have to do laundry, right? Well, I guess you don't have to, but so how many local maxes do I have here? 2. How many local mins do I have here? 2. Do I have an absolute max here?
Infinity.
Okay, so no, right. So whenever we're talking about what height are you at, right? If you say infinity, I'll call you back and say keep climbing. So we want to, anytime we're saying an absolute max, we should be able to tell what the height is. And clearly there is no maximum height here. It just keeps going up over and over again, right? Oh my God. I'm so bored. Oh, here's the interesting one. This one, it's asking, is it even or odd? So remember, even is going to be symmetrical this way. Odd is going to be symmetrical this way. And so this one is neither, right? This is neither even nor odd. And it's asking for intercepts. I don't even know if you have to do this one. This is an exponential function. And so the interesting question on this is, what's the domain, right? What's our domain here? So you can see, and I'll zoom in on this graph. You can see that this graph has a horizontal asymptote of positive 4, right? And so the domain is going to be open 4 and up, right? Let me just write it this way. If I've got y equals e to the x plus 4, I've got that particular graph, 1, 2, 3, 4, and it's giving me this curve here, okay, and my domain is 4 to infinity, right? There's a horizontal asymptote that it never gets to. So that's it for that homework. I'm sorry I wasted so much time on it, but just try it. Ask me questions.
Professor?
Yes, Ryan.
Can you type in the domain there? Because I think yesterday I tried it, but...
Sure. So intercepts 0, 5 is only, right? Right, you're right. Ryan, you're asking me just to answer the questions here, right?
Yeah.
Yep, no problem. And then the domain is all reals. So it's asking me from minus infinity to infinity. So I'm using open parens. Oops, get in the box there. Open parens from negative infinity, comma, to infinity, close open parens, enter. So there's my domain. So it could have been that you use square brackets, right? So remember the round brackets, I can't get there. Square brackets, I can get there. So it could have been that. Range, we had already said from 4 to infinity. And then where is it increasing? Everywhere, right? So I don't need to keep going here. I think, right? Am I right, Ryan? You're okay there?
Yeah, I'm okay.
Nice. Daria, question?
I was wondering what homeworks are we supposed to have done by now?
So today we're on homework. I forget. Where am I? Oh yeah. Today, so if you can see, I've got my homeworks all with numbers on them, but it's easier to look at the homeworks and to look at what is chapter 12, what is chapter 2, because that's the first test. So, but I would say after today or by Friday, you should be at least up to homework 11 or close to it, right? Remember, I'm going to teach the last section of chapter 2 on Friday, and then you have a whole week before you take your test. But hopefully you get questions answered Monday and Wednesday, right? And of course, office hours, right? I don't do office hours on the day of a test because oftentimes I have just panicked students, and if you don't know it on the day you're going to take the test, you don't know it. So let's get things done early, right? So, right, the morning class wouldn't have an office hour before their class anyway, right? And why the hell would they go to an office hour after a test? I like to give tests on Friday or the last day we see each other in the week so that you can then take the week off, right? You just took a test in pre-cal, catch up on another class, go to a movie, clean the room, whatever you need to catch up on. You certainly don't need to be doing pre-cal homework after you take a test, right? It's like dessert. I'm not going to eat anything else. All right, piecewise functions. This section sucks, but it's important. It's important especially for where you're going, which is the calculus class. So piecewise functions. So this is 2.4. It's the only section of 2.4. And then we have one last section of chapter 2, 2.5, which is on transformations and translations and transformations of functions. Pretty easy. So 2.4 piecewise functions. Basically, there's a couple of problem types, but we should look at what a piecewise function is. So let's look at the most famous one there is. F of x is the absolute value of x, right? And so this is a two-piece function, but it's always going to be double that. So if I have a three-piece function, there's going to be 6 pieces I'm talking about. If it's a two-piece function, there'll be 4 pieces. And those pieces are what's the function and what's the domain, right? So I'm going to have a function of x on a domain of x is greater than 0, and a function of the opposite of x on the domain of x is less than 0. And so this is a two-piece function, right? I'm always talking about my function pieces, right? So y1, y2, and then their domains. Right, so those stacked left pieces are the machines. In this case, lines, y equals x and y equals negative x. And those stacked pieces on the right are the domains of each of those machines. Right, and so of course we know what this particular function looks like. When x is positive or 0, I have y1, and when x is negative, I have my y2, right? So we see that piecewise, that absolute value function. And of course, you can see I'm just taking this green part of the line and making it positive, right? So the absolute value takes all the negatives, makes it positive, and it doesn't touch the positives, right? So if my x is positive, leave it alone. If my x is negative, negate it to make it positive, right? And so basically what we're seeing here is the whole thing. We're seeing the whole thing here in what am I going to ask you? I'm going to give you a piecewise function. You should be able to graph it. I give you a piecewise function. You should be able to evaluate it. You should be able to find domains and ranges and et cetera, right? And so, and the real connection for us is in calculus is, do the pieces connect? If they don't connect, we're talking about being discontinuous. Do they connect with their slopes? We're talking about, are they differentiable? So if you imagine this one as a ride, right? Can you imagine like Great Adventure or whatever the hell they are, right? I'm afraid of heights and widths, so I don't go on rides, and rectangles freak me out, right? So, but if I'm on this ride, you can see I've got a real sharp point there. So this one we would say is not differentiable. I want a nice smooth curve to be differentiable. And of course that derivative I'm talking about is a slope, so I'm talking about tangent lines and all of that. So, so we use piecewise functions quite a bit in calculus, right? You know, my machine's got to do this, and then it's got to do that, and then it's got to do that, and do all of the pieces connect. That's what we're talking about. So let's jump to a problem here in 2.4. Is this okay? Everyone comfortable here? I can imagine that there could be some discomfort here, and I've got my chat on. So if you want to say something but don't want to say it out loud, that's fine. So everybody's okay here with this piecewise thing, but it kind of gives you a little feeling like, at least it did to me when I was learning this stuff. I'd be like, ugh, I don't like this. But maybe you say that about everything anyway, right? All right, let me look at a homework problem. So this is homework 11. piecewise functions. I always thought if Tolstoy was a mathematician, his book would have been War and Piecewise Functions. Thank you. I'll be here all day. Actually, I'm not. I won't. All right. Here's my function. I've got a 3-piece function. The machine is x squared on the domain of negative x values. The machine is a single height of 0 on the domain of x is 0. And the function is 3x plus 1 on a domain of positive numbers, right? So I want to graph it. I'm usually going to ask you to graph it. I'm going to ask you to evaluate. I'm going to ask for domain. I'm going to ask for continuity. Doubtful, I'll ask for differentiability. Differentiability is a calculus concept, but it simply means the slopes are matching up. Or it's a smooth ride. It's a kiddie ride. So I have my function, so f of x equals a 3-piece suit of x squared when x is less than 0, 0 when x equals 0, and 3x plus 1 when x is greater than 0. So first thing I'll say is let's graph this. And I'll show you how to graph this on Desmos, and I'd like you to do a quick Google search on graphing piecewise functions on TI-83, 84, whatever you're using. And so certainly I know what x squared looks like, right? But it should be pretty clear that I only want this piece, right? So this red piece, oops. So the red piece is not there. So there's my y equals x squared. Right? So you certainly can graph the whole thing and then realize what part you have to erase based on your domain. Right? Based on your domain. The next point is 0, 0. Right? So 0, 0 is on my graph. And the last point is y equals 3x plus 1. And I'm simply going to graph that. When x is 0, I get a 1. And then there's my slope of 3x. So pretty darn easy to graph piecewise functions, right? Either it's a mother function. Go ahead, yeah.
Is it supposed to be closed or open?
So the green is open because of no equal. Oh, thank you. You're right. All right, thanks. Yeah, so no equal sign means open. With an equal sign, fill it in, right?
But even if there's no equal, we can't plug in 0, right?
You can. You got to pretend you don't know you can't. And it's a limit, right? If x got really, really close to 0, right? Like if I'm doing x's and y's, right? And I'm doing 0.1, 0.01, 0.001, 0.0001, right? It's pretty clear that this thing is going to 1. And so I just say, well, let me just forget that I can't plug it in. Let me just plug in 0. So there's my piecewise function, but the actual problem says to me, find f of -2. So the question is now, what machine do I use? My first machine, my second machine, or my third machine? And so when x is less than 0, I'm going to use that first machine. So -2 into x squared is going to give me 4. So when I plug in -2, I get a height of 4. And then it asks me for f of 0. Well, of course, anytime I plug in 0, I have to get 0 out by my rule, by my second machine. And then it asks me for f of 2. And that, of course, is my third machine, 3x plus 1, so 7. So kind of offensive, but so what? Take it, right? Because of the problem we just did at the beginning of class, not easy, right? And now we'll take a couple of easy problems every now and then. So if I give you a piecewise function, graph it. If I give you a graph, give me the function. Evaluate, find a domain, range. What's my domain here? Look at that green part. Yeah, everything, right? So the domain here is negative infinity to infinity. What about my range?
Would it be -2 to infinity?
So now we're doing shadows on the wall, right? So I'm saying, okay, cast the light this way. Where will it hit on the wall? So the lowest it hits is 0, right? And inclusive. So the lowest height I hit is 0. And then how far up is that green or black going? Going all the way up, right?
Infinity.
Yep. And is there any gap in the casting of the shadow on the wall here? No, right? So if I cast my light this way, it would shine through, so there'd be no shadow. But if I cast my light this way, I would get a shadow, right? So I have to look at, at all of the y values that I would hit. I like to think of it as a imagine I could take a basketball, right? So I'm holding the basketball up in the air and the light shining down. What do I see on the ground? I see a disc, right? So I imagine I could take the basketball and push it into the ground and it won't spread out. It'll just push into the ground and it will show me everywhere it hit the ground, like a shadow, a circle, a disc, right? So same thing with my graph. When I'm doing my domain, I'm pushing down and asking where did it hit the axis. And when I'm doing my range, I'm pushing right against the wall and saying where did it hit the y-axis. And that's the type of learner I am. I'm visual. Like when I learned to play music, reading notes, not easy for me, but if I watch someone play it, I could play it, right? So I'm also auditory, so I could hear something and then play it. So but like reading it is not for me. So I'll stress geometry a lot, right? I'm interpreting the book so that when you're reading the book, you're getting it, but then you're maybe hearing my voice and I'm trying to say it in a way that makes common sense, right? So, but you're a student, you should by now know how you learn. What's a way that you learn, right? So there's lots of learning styles, right? So I could never miss a class because missing a class for me meant reading the book and it sucked, right? So 30 some years ago, there was no YouTube where a bunch of nerds on there explaining everything. So let's do another problem here, piecewise. Yeah, this is okay. No, let me go more difficult. Oh, I'm supposed to give you a piecewise on. I'll do this one. I'll do this one, and then I'll put it on Desmos. Go ahead, Ryan.
Well, I was gonna say the next one is even harder.
Really?
No, there's like one big asks you to.
With the one that gives you the graph first, right? Yeah, I'm gonna do one like that too. If that's what is that what you're talking about? Well, the one that gives you a graph only.
Yeah.
Yeah, I'll do one like that too. So let me do this one. Okay. So I got a 3-piece here. I'm gonna find the domain. I'm gonna graph it. I'm gonna find the domain. I'm gonna get intercepts. I'm gonna find the range. I'm gonna talk about continuity. I might even talk about differentiality, even though that's calculus. And you'll see, calculus is so easy. You're going to love it. This class sucks. Nothing I can do about it. I got to torture you so you're ready. So I've got a 3-piece function here. I've got the first piece is y equals x plus 5 from -4 inclusive to 1. I've got the singleton point at x is 1, 9. And I've got the function 2 minus x when x is bigger than 1. So kind of similar to the last one, only the last one had a curve, right? y1 was a curve. Here I've got 2 lines and a point, right? So I want to graph this, and it certainly can graph x is 1, 9, 3, 6, 9, right? Pretty darn quickly. So I've graphed my middle machine, my middle function. I can graph y1 by picking 2 points, and usually my domain will demand, is the best way to think about which points I'm going to pick. I'm going to pick x is -4 and x is 1. I don't have to, but that's typically what I choose most of the time. So when I plug in a -4, I get a 1. When I plug in a 1, I get a 6. 3, 6, 9. So I get an open point here at 1, 6. At -4, 1, 2, 3, 4, I get a -1. And note that that line would normally keep going, but because they've restricted my domain, right, I'm going to just stop it there. How are we doing here? Nice. Nice. Awesome. All right. So now my third piece, I have an x and a y3. And I'm using this one now, and I'm going to use 1 and any other point too, right? So when I plug in 1, I get 1, 1, 1. And when I plug in 2, I get 0. And there's my y1, right? So this is y1, this is y2, this is y3. And there's my...
Professor Guar.
Yes, yes.
For the third function,
yep.
Are we allowed to plug in 1, even though it says 1 is greater than...
And so,
1?
yeah, so when I'm doing that, like when I'm calculating this piece, in my brain, I'm doing calculus. I'm going, okay, let me get really close. So like 1.1 or 1.101 or 1.001 and 1.0001. And so I'm calculating where am I moving that line to if I got to 1. And of course, I can just pretend I'm allowed to put in 1.
Oh, okay.
And that's what I'm doing. Right. Nice. Domain. Squash it onto the floor. What's the furthest left x value I get? Right? Squash everything onto the x-axis. And where is the ink at? Right? Range. Everybody okay there? Squash everything onto the wall now. I got an issue. It looks like I'm going to go from -infinity up to 6, but not including 6, and then I want to add one other point, right? Union the singleton 8, or 9, sorry. Right, so when I squash this stuff onto the wall, right, I get an open point there, but when I squash it this way, I fill it back in again. Right, so I'm squashing everything onto the wall. And there's no blood or guts dripping down, right? You're just imagining it doesn't spread out, right? Like if I pushed a basketball into the ground, it would start to get wider and wider and wider. We're pretending that doesn't happen, right? Just goes perfectly smooth into the floor. How are we doing here? Nice. Continuous or not? What's your gut say? Is this continuous?
The first one, no.
No. So there's holes in it, right? And all I'm thinking is roller coasters. If I'm riding on this roller coaster, am I dropping through at any point, right? So yes, there's a hole in it, not continuous. We'll be asking, like, at 1, is there a limit? So, right, the limit as x goes to 1 from the right of f is 1. But the limit as x goes to 1 from the left of f is 6. So I'm asking, do those things meet up? No. So no limit. There's no limit at 1. Is it differentiable? Can you imagine this ride being smooth? Hell no. Right? No. So this guy is smooth, right? At no point do the tangents jump away from each other, right? But this ride here is, so this one is diff, right? It's differentiable, meaning the slopes are nice and they're related to each other. But on this one, the slopes are not. Look at this slope. Positive, 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 positive. And then all of a sudden, negative, 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 negative. Right? So if you can imagine what happens on that ride, right? You have that drastic change. It's not a smooth ride, not differentiable. This is all calculus stuff I'm talking about. All right, I got 2 minutes, sorry. I want to do one more problem. I'm going to run out of time. How about this? We just stop now and I say the first recording I post today, the last problem is the one that Ryan was talking about at the end. If I give you a graph, how do you come up with the piecewise function? So at the end of the first video will be one of those problems if you want to look at it. If you can just do the problem without looking at it, good for you. So Friday we're going to come in with our phone view, testing view on the when you come in, and I'll say Jamal, that looks good. So and at that point you can turn off your phone and come back into class as you wish, right? Or I'll say, Elise, that can you get the camera a little bit higher, right? I'll say, Elmer, I can't see your desk, right? Something like that. And then once things get adjusted, and I'll say, good, okay, at least that's good now. And then you can leave and come back in to the class for the last lecture on chapter 2 in whichever way you choose to do that, right? All right, we all good? We all good?
Yes, sir.
Nice. I'll stick around if anybody needs me. Okay? Stick around for a minute. Otherwise, see you Friday. Have a great day.
See you Friday, Professor.
See you Friday.
Thank you, Professor.
Thank you.